Hello, everyone. Welcome to my talk. My name is Sicheng from East China Normal University. This is my first time in Kai. I am excited to share our work on automated question answering for graph visualizations. Graph visualizations are widely used to analyze topological data and support decision-making tasks. However, it is not an easy task for users when there are many complex analytical questions about graphs. First, users need to understand the question before observing graphs. When observing the graph, users also need to understand the legend and textual information, perceive graphical data, analyze the community, calculate the degree values of the data, and other steps according to the different questions. To address these problems, we propose a pipeline to answer natural language questions about graph visualizations, and generate visual answers to help users analyze data and make decisions. We conducted a formative study to understand what questions people would ask about graph visualizations and how they ask them. We finally collected 561 valid question-answer pairs. We define a question to be lookup if its answer can be found directly within the graph data. These are typically simple questions that only require information from the GML files, such as asking for a node's neighbors. Compositional questions, on the other hand, require knowledge base expansion, which we will introduce later. We also classify questions according to their utterance into two types of questions, semantic and structural. We have open-sourced our collected dataset. The traditional method is only appropriate for simple charts, such as bar charts and line charts. Graphs have more visual attributes than the above charts. It is hard to convert graph visualizations into tabular data. To solve these problems, we design a pipeline to convert graphs into knowledge bases, and apply a novel reinforcement model to adapt it to visualization question answering. The pipeline includes 5 components: extract primitive triplets and build knowledge bases, knowledge base expansion, topic entity extraction, automatic question answering, and visual answer generation. In the first step, we convert the input graph to GML format and extract topological data and visual attributes. Then, we design a data structure in the form of KB triple for graph visualizations. These data originally existed in GML, so we call the extracted triples as primitive triplets. In order to answer more kinds of questions and improve the generalizability of our system, we designed a KB expansion module in our pipeline. There are two aspects of extension: one is the semantic extension, and the other is graph analysis extension. In semantic extension, we use WordNet to first find all synonyms for relations, and artificially designated multiple aliases for the relations. Our system utilizes a semantic description file containing configurable semantic information. This description file can be populated beforehand by graph providers, and can also be updated by users with an editor to expand semantic information. In graph analysis extension, we calculate the frequently used graph attributes and add them to our KB. The third module is to extract topic entities from the question. Topic entities are tokens in the questions that are grounded entities. They will be used to generate query graph in later process. For example, Courfeyrac is a topic entity of the question: what is the number of people that co-appeared with Courfeyrac? First, we utilize NLP framework FLAIR and the SOTA NER model FLIRT for named entity recognition. Second, we tokenize the question, generate n-grams and match all n-grams with entities in our KB to prevent the NER model from missing topic entities. Third, we design a connective word matching step to extract entities related to edges. At last, as all the questions are relevant to the graph, if the graph entity is still not present after the above steps, we will add the graph entity. To query the correct answer out of the knowledge base, our Candé model needs to generate a query graph containing a core relation path that starts from a topic entity and ends at the answer node. For each iteration, we try to extend each query graph. This can be done by extending a feasible relation to the graph or an aggregation operation. We predefine 3 keyword lists as shown in table. If a keyword is detected in the question, an aggregation operation will be added to the query graph. For the candidate query graphs, we rank these query graphs by a reinforcement learning model. We train this model on a large dataset of questions named complex web questions and a large knowledge base named freebase. We generated a 6-dimension feature vector, and feed the feature vector of each candidate query graph into a fully connected layer of the reinforcement model to obtain the policy function. After the aforementioned process, we obtain an optimal query graph for the question. By generating a SPARQL query from its core relation path and executing the query in the KB, we can obtain the textual answers. We then design an answer generation module to provide intuitive and insightful answers to the user. GVQA's answer is composed of 3 components: textual answers, visual answers, and auxiliary answers. In terms of answers presentation, we design entity highlighting, subgraphs. An information card entity highlighting is the commonly used method, where we render red borders and shadows for the entity, scale up the node size or edge width, and display the label beside it to make it more noticeable. Highlighting a community will highlight all the nodes and edges belonging to it. Subgraphs are also designed for communities. We take the nodes in the community and the connections between them and form a separate subgraph for presentation to the user. Info cards contain commonly concerned properties, such as labels, degrees, or centralities of the entity.
Now we look at some real cases. We have populated some graphs collected by Mark Newman into our system. The first graph is Les Miserables, which is a co-appearance network of characters in the novel Les Miserables. First, we want to know which node has the highest node degree in the graph. As we can see, the answers is obtained here. Also, if we want to know what bridges does the graph contain, and then the bridge edges will be highlighted as well. Now we turn to a semantical question. How many characters are there in the graph? Here we successfully acquired the answer. Another question with semantics is, what is the number of characters who co-appeared with Valjean? It is essentially asking the degree of the node Valjean, but since our knowledge base is semantically extended, we can solve this too. To see what our characters are they, we can further ask what characters could appear with Valjean. These characters are now in the textual answer area. We can try to ask something about the edges, but in a semantical way, such as how many times did Valjean and Cossetti co-appear? And our system gave us the weight of the edge and highlighted it, and put the edge and the node it connects in the auxiliary answer panel. Directed graph about political books, whose directed edges mean the book co-purchasing. So if we ask which node has the highest out degree in the graph, whose answer means that this book will be most likely to make many readers buy another one, the answer is arrogance. Now if we ask what is the node with the highest in degree that links with arrogance, we now know that among the books that drove people to buy arrogance, Off With Their Heads is the book that most likely to be the purchasing destination. Lastly, we look at a large graph. NetScience is the co-authorship network of scientists working on network theory containing 1,589 nodes. We first ask what is the node with the highest centrality. As we can see, our system has done a good job in this task and provided these useful auxiliary answers. Next, we are curious about which node has the highest degree that links with Barabasier. We get the answer of join edge, and the auxiliary bar chart has become the degree rankings of Barabasier's neighbors. How about the weight? We ask, what is the weight of the edge between join edge and Barabasier? We got 4.225. Now we turn to the communities. We may ask, how many communities does the graph have? Though no highlight is provided, we get the textual answers and a small overview for each community as displayed on the right. If we want to know which community includes Barabasi, we can directly ask which community does Barabasi belong to. The entities inside the community will then be highlighted, and we can check the community size, average degree, and the other computed properties of the community here.
Comparing our work with past chart question answering works, the main difference is that GVQA is based on a graph-based database querying, while TableQA is based on a relational database. One of the main differences is that graph databases store the relationships between data as data, whereas relational databases infer relationships between columns of data tables. Another difference is that graph databases are often more flexible and scalable than relational databases. Graph databases do not rely on fixed table schemas, so they can handle data that is structured in complex or evolving ways. Most of the graph visualization questions focus on the complex relationship between nodes, which makes graph-based databases more suitable for graph visualization, while relational databases are better suited to applications that involve more structured data, such as bar charts and line charts. The current pipeline of GVQA system retains some limitations. We did an error analysis in the evaluation. The failure to answer the question mainly stems from the query graph output error of reinforcement learning, the failure of semantic extraction, and the information not existing in the knowledge base. In the future, we plan to expand our work in 3 directions. First, the current version of GVQA cannot answer true or false questions and some reasoning questions with advanced semantics. Some of the latest breakthroughs in NLP may be able to solve this problem. Second, we plan to add more types of visual answers, such as outputting different graph layouts according to different types of answers. Third, we are trying to extend this approach to more types of diagrams that have not yet had mature works, such as geographic visualizations. With this, I would like to end my talk. Thanks for watching. If you are interested in further communication, please feel free to contact me.